Hey everybody, Phil Plait here from badastronomy.com, and I'm holding yet another Q&BA where you guys get to ask me questions about astronomy and space and whatever, I guess just science. If I don't know the answer, because I don't know the answer, I'll let you know. I'm better at the space and astronomy stuff. But this is a lot of fun. I like doing this every week, and I think Sundays are working out pretty well for me. It makes it a little bit easier. I may try different days. For example, when my daughter's at school, then I know she's not using her computer, and that makes my stream look better. So who knows? And some people are complaining, saying, it's already Monday on the other side of the world for me, so it's hard for them to do it. And if I want to balance this out and not be Western Hemisphere, Northern Hemisphere biased, I should do this on another day. But we'll figure that all out. Maybe I'll start doing this twice a week. I don't know. But this is basically just an hour. It's on Google Plus Hangouts. It's recorded to YouTube. So some of you folks are watching this live right now, but I would expect sometime in the future people will be watching this on YouTube, so it's like time travel. Okay. So if you've circled me on Google Plus and you're watching this, or you're on Twitter, you can ask me questions there. If you have circled me on Google Plus, please +1 this chat so that I can see how many people are in the room. That helps a lot, just to know. Are there 10 people in here? Are there hundreds? So that as I'm looking through the questions, it's easier to pick them. If I see the same person asking a bunch of questions over and over again, if they're the only person in the room, I'll answer those questions. Otherwise, I'll answer everybody else's. So I will refresh the chat room page. There's nothing on Twitter yet. And here we go. So, and right away, we got a good question. In fact, this is such a good question, I may actually answer it. One of the things I do is, this is an hour long, and I'll put this whole thing on YouTube, so if people are like really bored or whatever, they can just sit and watch it. But if there's some good questions that I know I can answer succinctly, like that ever happens, I can edit them out and put them on their own separate thing, and then I can have an archive of single questions that are answered, and I think that helps a lot too. And that way I can link to when people say, oh, I'm going to ask this question. I say, yeah, already answered that. Should I wait for that's my dog, Canis Major. You can probably hear her outside. Okay, probably a squirrel. Nope. All right, well, that's live. That's what happens. So, I really don't want her barking in the background, though, while I'm talking, but I guess there's not much I can do about that. So, all right, so here's a great question. So I'm going to answer this like it's going to be a short thing, which means I reset, make a short announcement, and then go into it. Except I really can't. Hang on just a moment. Let me put the splash page back up. I apologize for this, folks. She's done. That's good enough. Yeah, I'll edit this part out. Okay. So it's just me there. All right, good. So here we go. Hi, Phil Plait from badastronomy.com here with a Q&BA session where you guys get to ask me questions about astronomy and space. I have a great question here from John Fleshman, and that is, Phil, what would you tell someone who asks why we spend any money at all for NASA instead of here on Earth taking care of our local problems? I think we need NASA and space exploration, but couldn't come up with a good answer last night. This happens a lot. Somebody asks you a question, you know the answer, right? But right there, right on the moment, on the cusp of the moment, you can't think of something. It happens all the time. It happens to people very familiar with things. One thing that helps is if you think about these questions a lot, read about them a lot, and even practice answers, or look for answers that are short and sweet and easy. In this case, there are a couple of different ways to answer it. When somebody says, why are we spending money on NASA when we have local problems here? Okay, the short answer is, when we spend money on NASA, it's not like we're loading a rocket full of dollar bills and just exploding it out into space, right? That money is being spent on space, but it's being spent here. There are people who are employed by NASA all over the country. NASA has research centers in Maryland and Texas, in California, all over the country. And they employ contractors who live all over the country. And there are pieces being developed for the rockets that are being built in Utah and Alabama, just all over the place. So that money is being spent locally. Now, for example, astronomers might have NASA grants. And so they might be getting a few $1,000s to do some research with, say, Hubble data from 10 years ago. All that data is archived. So I could propose to NASA, hey, you know what? I need 10 grand to pay for myself for a little while to work on some of that old data because I'm looking at variable stars and I want to go back into the archives and find all that stuff. So that money's being spent wherever I happen to live, and I have to pay taxes on that. So that money goes back into the economy. And so that money is being spent locally. Also, that's the short answer, and you can make it as short as you want. The more philosophical answer, the longer answer, is that we don't want to be eating our seed corn. And that's a great expression. What that means is if you're planting corn for next year, you have seed corn for that time. The thing is you have it now. And if you want to plant it now for next year's corn, then you're planning for the future. But if you're out of corn now and all you have left to eat is your seed corn, great, you can eat that now, but then what are you going to do next year? So you don't want to do that. You want to plan for the future so that you can always have something set up for the future as well as the present. And that's what investing in science does. It's not just NASA. It's the National Science Foundation. It's all these different science organizations that are sponsored by the government. These groups are doing work, and they're laying the foundation for the future so that we can learn more about the Earth, our environment, the sun, the universe. Sure, that benefits us in many ways. It helps our technology. Everything, you guys are listening to me right now because of technology, and that technology is based on science, and that science is a tapestry, a mosaic of hundreds of thousands of different individuals who have contributed to it. But also, it inspires the next generation. You know, the technology you're using now is based on science that we've done in the past. We have to continue to produce that science, to do the research, so that we can continue into the future, right, to have the technology we enjoy and to learn. And that's just, I was going to say Machiavellian. That's sort of, I don't want to say, egotistical is the wrong word too, but I mean, it's the technology that we're using now. And it's not just technology is what I'm trying to say. It's not just sort of that banal use of science, that it just, our technology depends on it. It's also just the love of mystery, the love of problem solving, the love of science, the love of nature, the love of looking around that corner and seeing what's next, what's over the next hill. That's what this science does. It's going to encourage the next generation of people who want to explore and who want to learn and who want to find out what's going on in the universe around them. So when somebody says, why should I spend money on NASA when we need that money here? That's a false dichotomy, okay? We need to spend that money for the future. That money does get spent locally. That's very important. And also, we can do both. You know what? Yeah, right now as I talk, we're in a recession or an economic downturn or whatever the heck you want to call it. But in fact, we can choose to spend money in different ways. And we choose to spend millions of dollars an hour on foreign wars. And we choose to spend $90 million a year on tobacco products. That's one of my favorites. We can choose to spend that money on science and investing in the future. It's our choice. Make the right one. How's that? There you go. So what I'll do is, like I said, I'll edit that out, and that'll be its own separate thing, and it'll be part of this whole thing too. So, let's see. Let me check Twitter. And let's see, Twitter. Sorry, I know as I'm reading through these, you have to look at my giant shiny forehead. Oh, here's a good one. You see, the problem with Twitter is people's names are all, you're not allowed spaces, so it's hard to tell what somebody's name is. And this one is from Verethele, Verethle, V-E-R-E-T-H-E-L-E. And she asks, according to her avatar, it's a woman, any advice or information on how biologists can become involved or are involved in space exploration? Absolutely. Astrobiology is the marriage, right, of life sciences and space scientists, I suppose you'd say, because we are now going to other planets. It used to be that Mars and Jupiter and its moons and all that were just lights in the sky, but now we understand that they're worlds. I mean, we've understood they're worlds for a long time, but we're going there, and we're studying them more as worlds on their own, as opposed to astronomical objects of interest. And it's kind of a funny psychological shift from a light in the sky that belongs to astronomy to a world that belongs now to geologists and planetologists and atmospheric scientists, and now biologists. Oh, her name is Autumn. Hi, Autumn. So now we want to know about the origins of life and the evolution of life, how life can start and what happens after that, what happens in different environments. So there are a lot of biologists who are employed, again, by NASA to learn about this. And it's not just that they're looking at possible life on Mars or Europa or Saturn's moons of Titan and Enceladus, where the conditions may be right for life, even though it's very cold. We can look here on Earth, and there are these extremophiles, these bizarre life forms that live, for example, underground in caves. I actually went into a cave in New Mexico and scraped a little bit of this stuff off a rock, and it's a bacterium that lives extremely slowly. It basically digests the rocks and uses the minerals from the rocks for its own life process. And they're incredibly slow metabolism. It's bizarre that they can do this. But the more we learn about those weird things, the more we could stretch our imagination and extrapolate that to life on Mars, where it's very cold. Chemical processes may not occur as rapidly on Mars as they do here because it's colder. I know that's an oversimplification, but it's an interesting thing to think about. So how could life arise there? There are these vents down at the bottom of the ocean that are spewing out what we would consider toxic chemicals at temperatures that would kill us, even if the pressure weren't 1,000 times what we're dealing with the Earth's air here. And yet life thrives there with this boiling sulfur coming out of these things. And there's all kinds of crazy stuff down there. And so by learning about that, again, you find out how life evolves to fill different niches. And that's a fantastic use of biology. Pardon me. So that's one great way to do that. And it's not just NASA. There are other organizations, NSF. I don't know about the European Space Agency, but I assume they have something to do with this. I'm not as familiar with them as I am with NASA because I live in America, and I'm a big ham-fisted American, so I don't care about other countries. It's a joke. So that's something you can look into. I think that's a fascinating field. I'm not a biologist. My knowledge of biology is that of an interested layman who is educated, probably, as my wife likes to say, I'm educated beyond my intelligence, educated in other fields of science. But I really enjoy reading about that kind of stuff and reading about the biology of other planets, and I think that's really cool. Let's see. Okay, I think that's everything in Twitter that I can see. So let's go back to the Google Plus chat page. Oh, here's a good one. This is a very common question, and I may have to do this one as a separate Q&BA as well, because I get asked this a lot. I've written about this one, and there's lots of web pages about it, and it turns out there's a lot of misconceptions about it. Hopefully I can answer this off the top of my head without too much Sturm und Drang here. Let me think about this. Yeah. I was wondering, what I can do, too, is put up pictures, but I don't think I have a good picture for this one, and you wouldn't want to see it anyway, trust me. So here we go. Hey, Phil Plate from badastronomy.com here, doing another Q&BA live chat session, and I got a great question from Jeff Grams, who says, I'd like to ask about the effect of the minus 203, let me try that again. Let me just start over. Makes it easier for me later. Hey, Phil Plate from badastronomy.com doing another Q&BA chat session. I got a great question from Jeff Grams on Google+, who asks, I'd like to ask about the effect of the minus 273 degree cold in space on a body without a spacesuit. Does the heat need to leave your body into something? In what way would it be different to a severe cold burn received here on Earth? This is a great question. You get this a lot, especially since movies show astronauts sometimes, like the movie Outland, and there are a few others. I think Mission to Mars did this, where somebody opens up their spacesuit when they're out in space, and then something horrifying happens. In Outland, they would explode, literally, and you'd see what looked like somebody throwing pizza sauce inside of the spacesuit. It was nasty. In Mission to Mars, a guy opens up his spacesuit helmet, and he freezes instantly. You know, would these things happen? In a word, no, that wouldn't happen. First of all, you wouldn't explode, right? When you climb to the top of a mountain, you don't explode. It doesn't work that way. If you were to, say, go out into space in your spacesuit, and you were out, I don't know, far away from the sun, where it's really cold, and you open up your visor, what's going to happen? Well, all the air is going to rush out of your suit, and you're going to decompress, and that's really awful. It's a terrible feeling. You'll get the bends. Your blood won't boil. This is another thing people think. The blood won't boil because your blood is encased in all your veins and arteries. It's a closed system. And so even though like water, for example, will boil at lower temperatures if the air pressure is lowered. Where I live in Boulder, water boils at less than 100 degrees centigrade, or Celsius, I suppose, is the correct unit, less than 212 Fahrenheit, because we have a lower air pressure here. So you might say, oh, if you go out in the vacuum of space where there's no air pressure, maybe your blood will boil. But it won't, because it's all contained. It's in an airtight unit, your circulatory system. But things will happen. You will erupt out. All of the air in your lungs will come out of your mouth. All the air in your intestines, in your lower tract, will find a different escape route, for example. I'll leave that to your imagination. The fluids in your mouth, your saliva and all of that, will come out of your soft tissues, for example, around your lips and your tongue. That will be drawn out, so you'll get very dry cracking in there. But that's the least of your worries, because basically you're going to black out within a few seconds without any air. There are all sorts of horrifying effects that happen then. This has been studied because there have been accidents. For example, a Russian cosmonaut was in a barometric chamber where they let all the air out by accident, and they were able, it was some time before they could get it back up, and they were able to study what happened to him. And there are spasms that happen, and seizures, and you go into a coma, and the blood vessels in your eyes will burst, because those are near the surface, and they will feel that difference in pressure. It's really, really horrible. But the question here specifically is about the cold. What happens with the cold, right? Well, here on Earth, if I grab an ice cube, right, I can feel that cold, and the heat from my hand transfers through touch into that ice cube. That's called conducting. The heat from my hand is conducted into that ice cube. You can think of it as the cold being conducted from the ice cube to your hand. That's not the way we do it. That's if you work out the math, if you do the physics and math of it, that's a perfectly acceptable way to do it. But a better way to think of it is that heat goes from a hotter source to a colder source. So your hand's heat gets lost, conducted into that ice cube. The same thing with air. Okay, our bodies are at a temperature about 37 degrees Celsius, and the air around me is at about 22 degrees Celsius. I am conducting that heat into the air around me. But it turns out that's a relatively efficient process, but it depends on the densities, in one sense, of the two objects. Ice is dense, my hand is dense, so when I hold onto an ice cube, I'm really conducting that heat very rapidly, and so I can really feel that. If the air were as cold as that ice cube, the conduction between my skin and the air around me is not as efficient, because the air is much lower density than the ice cube. And that's why ice feels colder at, say, 0 degrees Celsius than air at 0 degrees Celsius. It's the same reason you can imagine when you stick your hand in a hot oven. Imagine you're baking a cake at, let's just say 350 degrees Fahrenheit. I don't know what that would be centigrade. Baking still, in America, still uses imperial units. If you've got a pan with a cake in it, and it's at 350 degrees Fahrenheit, when you reach your hands into the oven, right, the air feels hot, but you can take it. You could take it for several seconds, maybe even tens of seconds. The instant you touch that pan with the cake in it, you're going to get horribly burned, because the metal in that pan is solid and dense and can conduct that heat into your hands very rapidly, whereas the air does not. That's the difference between temperature and heat. Something can be at a very high temperature but not feel that hot, because it's not good at conducting that heat. Well, out in the vacuum of space, this is turning into a long answer, but it's, there's a lot going on. Out in the vacuum of space, there's no air. So there's no way to conduct your heat from your body out into space. So there's no way to get rid of your heat that efficiently. Now there's another way to get rid of heat. There are actually three ways of moving heat around. There's conduction, like I said. There's convection, where something hot will rise up. Like if you heat up a balloon, it will rise up through the air. When you heat water in a pot, that hot water rises up from the bottom of the pot to the top and cools off and sinks back down. That process, circulating a fluid that way, is called convection. The third one is radiation, to literally radiate away heat. Now your body is radiating away heat as well. As I'm sitting here again, my body temperature is higher than the air around me. I'm radiating away heat. But that's an incredibly inefficient process. It's much lower efficiency than the other two. Given the chance, the other two will dominate. But out in space, right, you can't conduct away that heat. You can't convect away that heat. There's nothing to convect around you. There's no air. So your body is forced to radiate away that heat. And that's a very, very, very slow process. So you will eventually freeze solid. But it won't happen in, a split second like it did in Mission to Mars. It will take hours. Now, you will feel very cold if you could survive somehow, if you had maybe an air supply, but you didn't have your pressure suit, and your ears weren't burst and your eyes weren't bloodshot and you weren't belching and out other ends and all that. You would very slowly freeze to death, but it would not be instantaneous. And in fact, what would happen is you probably wouldn't turn into like a big popsicle, a corpsicle. You would probably freeze dry because the air and the liquid would be leaving your body. The liquid in you're mostly water, right? That liquid would be coming out of your orifices. It would evaporate away, as well as getting very, very, very cold. So probably you would look like a mummy. You would sort of freeze dry. It would be really nasty. So there you go. An unpleasant topic, although it's kind of cool to think about. I really wish Hollywood would get this right. And in fact, a long time ago, I was asked by a writer about how this would work. And I was hoping that was going to get made into a program. It never did. But one of these days, it'd be an interesting murder mystery, I think, to have something like that. So there you go. So I guess to wrap that up, my advice would be, if you're in space, in your spacesuit, keep your visor closed. So there you go. That was really super long. One of these days I'll get a question, I'll be able to go, 6! And that's it. Oh, here's a good question. Adirondack Astro on Twitter. That's a tongue twister. How much study will be done when New Horizons reaches Pluto? Will we spend any time with the moons? Well, that's a really good question. And what I can do is open up a new window, New Horizons. New Horizons is a probe that launched, here we go. When did it launch? Oh gosh, there's so many probes out. I had this conversation with Emily Lakdawala, who works for the Planetary Society. She writes their blog. She's a journalist and studies planets, and it's so hard to keep track of all the probes. There's so many going. It's wonderful. Even with all these cutbacks, we're still getting a lot of stuff out there. The problem is the future. We're not building as many as we used to. So I'm worried that in 5, 6, 7 years, we're not going to have as many probes out there. But it is kind of nice to know that there's so many that it's actually kind of confusing to remember which is which. Here we go. New Horizons. It was launched, here we go, on January 19th, 2006. The principal investigator, the head banana, the top cheese, the top dog, his name is Alan Stern. He's a planetary scientist. He actually works here in Boulder. I've had some very interesting conversations with him about all kinds of different topics, including whether Pluto is a planet or not. I love tweaking him about that. He feels that we should have a definition of a planet that includes Pluto, and his reasons for it are very interesting. I won't go into it now because I'm going to be talking about this later on this week. I'm going to be writing about this, I think. So New Horizons launched in 2006. It's going to take about 10 years, just shy of 10 years, to get to Pluto. Let me show you a picture of it. Hang on. Let me show you a picture of it. Oh, I should probably just look at this on my website instead of on their website. Here it is. Oh, this is perfect. Here we go. Let me share this picture with you. So now you should be seeing my, there we go, that's perfect. You're now seeing my browser. And you can see this is New Horizons. It's actually not very big. I think it's about the size of like an office desk. You can see the dish here, that's the antenna that communicates with Earth. Over here on the right, this thing sticking out, these are RTGs, radiothermal, oh, for criminy sake, generators, radiothermal, radioisotopic thermal generators? I can't remember what they're called, but they basically use plutonium to generate electricity. There's a little tiny scrap of plutonium on it, and the fission of that plutonium generates electricity to power the spacecraft. It's traveling to Pluto, which is 30 times the distance of the Earth to the sun. So solar panels are of no use out there. The sun's way too faint. And you can see it has all of these different instruments, which have fun names. I love Alice and Ralph. If you're a Honeymooners fan, Ralph and Alice Cramden were the two stars of that old TV show. Ralph is a visible and infrared imager and spectrometer. So that takes pictures, which it'll relay back to Earth. It takes spectra, which means it breaks the light up that it sees from Pluto and its moons, breaks that up into different colors, and sends that back to Earth. And by studying that, you can learn chemical compositions of objects, temperatures, all kinds of things from that. So that's very important. Alice is the same thing, but it's ultraviolet. So Ralph looks in the visible and infrared, and Alice looks in the ultraviolet. That's important because the sun has ultraviolet light that hits Pluto. Pluto has a very, very, very super thin atmosphere of gas that is basically sublimated, turned directly from a solid into a gas off the surface. The sun's ultraviolet light is weak out there, but it's still enough to drive certain chemical processes. So by looking at that with ultraviolet spectrometer, hopefully they can learn a lot about what's happening. There's the radio science experiment, which looks at radio waves. Long-range reconnaissance imager, which is like a wide-angle camera, I guess. Excuse me, it's a narrow-angle camera, high-resolution geological data. That's right. I remember reading about this quite some time ago. So as it passes by Pluto, it'll be able to take decent images even when it's far away. There's something to study the solar wind around Pluto, subatomic particles around Pluto. Oh yeah, and the student dust counter. Gosh, I'd forgotten about that. This was a student-built instrument which, as Pluto moves through space, as New Horizons moves through space, it's whacked by dust particles out there, and this thing can count them up and measure the amount as it moves through the solar system. So it gives you sort of a map of the dust as this happens. New Horizons has been flying now. It's over halfway to Pluto, and so it's actually already gotten some interesting science. If you go to this website, if you look up New Horizons and NASA, you'll go to the New Horizons website on NASA's web portal, whatever you want to call it, and there's tons of information there, including a blog by Alan Stern, which is pretty interesting. He writes about milestones in the mission and what's going on, and it's actually really, really cool. It's going to fly past Pluto. There's no way it could bring enough fuel to slow down. I mean, 10 years to Pluto is super fast, right? This thing is moving billions of kilometers in just a few years. So it's really screaming out there. There's no way you could bring enough fuel to slow it down, to go into orbit around this tiny little object, especially since you'd have to slow it down almost to zero. Pluto has very little gravity. So to go into orbit around it, you'd have to really super slow down. So all it's going to do is fly past it. It's only going to be in the region of Pluto for a few days, and really close to it for only a few hours. So it's going to be taking lots of data as it does this, including images. We don't have good images of Pluto. It's smaller than the Earth's moon, okay? But it is, oh my gosh, 10,000 times farther away, I think, off the top of my head. That sounds about right, something like that. So Pluto is very, very, very tiny, even to big telescopes, and it's very difficult to know what the surface is like of Pluto, at least to map it like we do the moon, for example. So even our highest resolution pictures, Pluto's very fuzzy looking. So we're going to get our first high resolution maps of Pluto and its moons, Charon, Nix, and Hydra. Charon, Nix, and Hydra. And the fourth moon, which I don't think has been named yet. It was just discovered last year in a Hubble image. So and hopefully we'll discover more moons. One thing that there might be rings around Pluto. That's interesting to me. I wouldn't think that's likely, but there are some people who think that might actually happen. So it's going to study all that stuff in the few hours it has as it goes past Pluto. But it turns out that there are these other objects out there, these Kuiper Belt objects, which are basically giant frozen balls of ice. And they're interesting too, and they're hoping to pass by one or two of those once it gets past Pluto. And we'll see those close up as well. So it's a fascinating mission, and I'm a big supporter of it. I think it's really excellent. I love what it's doing. Okay, so that was Pluto. Let me go back to the room here. Oh, here's a question. I like this question by Keith Hallam. Is it true that relatively speaking, a human is hotter than the sun? I.e., if the sun were the size of a human, then its internal temperature would be less than that of a human, 32 degrees, 37 degrees Celsius. Hey, Phil Plait from badastronomy.com here, doing another live Q&BA chat session. And I got a great question from Keith Hallam, who asks, is it true that relatively speaking, a human is hotter than the sun? That is, if the sun were the size of a human, then its internal temperature would be less than that of a human. Now, this is a very common sort of an urban myth, a legend that I've heard, that if you were to scoop out a chunk of the sun and scoop out a chunk of human and compare them, the human would be hotter than the sun. But it turns out, no, that's just wrong. In Celsius, a human's body temperature is 37 degrees. The sun is 5,500 degrees, and it only gets hotter as you go deeper down into the sun. That'll be important here in a minute. I'll get to that. So it doesn't matter where you scoop out any part of the sun. It's going to be hotter than a chunk of human if they're the same size. But if you look at it a little more carefully, there's a more subtle thing going on, and you can ask about the amount of energy radiated away, or the amount of energy stored in a chunk of human and a chunk of the sun. And it turns out that when you do that, things change a little bit. Now, what I'm talking about here is what's called luminosity. It's the amount of energy an object radiates away every second. Now, the sun is very hot, and it's very big, and so it's very luminous. It turns out the luminosity depends on basically two things. How many square centimeters an object has, how much area it has. So, of course, the bigger it is, the hotter, the more radiant it is, the more luminous it is. And its temperature. Now, it turns out it's a constant called the Stefan-Boltzmann constant. Don't worry about that. It's just a number times the area times the temperature to the fourth power. So you have to do this in an absolute temperature scale. In Celsius is not one of those. You have to use Kelvin, which starts at 0 and goes up to infinity. In kelvins, a human being is about 310 kelvins. That's actually the unit. It's not degrees, it's kelvins. I know. Don't get me started. So a human is 310 kelvins, and the sun is about 5,700 kelvins, close enough. And you have to take that to the fourth power. So, of course, the sun is huge, has lots of square centimeters, times, right, its temperature to the fourth power, 5,700 times 5,700 times 5,700 times 5,700. Whereas a human has many fewer square centimeters, right? And you multiply that by 310 by 310 by 310 by 310, you get a much smaller number, which is why the sun is the biggest, brightest thing in the solar system, and 150 million kilometers away, it still feels warm, whereas a human can stand next to you and you don't poof, vaporize. So maybe we can even the scale out a little bit, and instead of just talking about total luminosity, do it per square centimeter. How much energy is the sun radiating per square centimeter compared to a human? Then we're comparing apples and apples instead of apples to oranges. And you can do that. You can take the sun's luminosity, divide it by its area, how many square centimeters it has, and do the same thing for a human. And what you find out is that, and I'm going to make sure I get this right, yes, in square centimeters, the sun wins. Oh, the sun is actually giving off far more energy per square centimeter than a human is, and it's by about 120,000 times. So if you were to take a square centimeter of the sun and compare that to a square centimeter of a human, the square centimeter of the sun is blasting out 120,000 times more energy. So again, the legend is wrong. It's wrong when it comes to temperature, and it's wrong when it comes to sort of, the amount of energy radiated per surface area. However, we can go a step deeper, literally. We can talk about volume, the third dimension. So instead of talking about the sun's luminosity per square centimeter, we'll look at it per cubic centimeter. We'll take the sun's total luminosity the energy it's radiating away, divide it by its volume in cubic centimeters. We can do that with a human as well. And I can show you about what a cubic centimeter is. Here's a mini marshmallow. It's roughly a cubic centimeter. I've colored it yellow to represent the sun. Here's one that I've left white to represent my pasty white skin. And if I take a cubic centimeter of sun and a cubic centimeter of human, then what happens? It turns out the sun is so big, it has so many cubic centimeters in it, that when you divide its luminosity by its volume, that number drops hugely. And the humans don't have that much volume, so their number doesn't drop as much. So it turns out in volume units, in cubic centimeters, who wins? The sun? Humans! Humans win. And it turns out humans win by a lot. A cubic centimeter of human flesh radiates away 60,000 times. 60,000 times as much as a cubic centimeter of the sun. So in that case, the legend is correct. If you scoop out the sun, you scoop out some human, and you say how much energy is radiated per whatever, and it turns out, on average, the human wins by a factor of 60,000, a lot. But there's one more thing to think about here, and that is I have averaged over the entire sun. And it turns out the surface of the sun is at about 5,700 kelvins. The core is about 15 million kelvins. Yikes! And that makes a huge difference, because when you take 15 million and take it to the fourth power, you just get a huge number. And when you do all the numbers, you take the luminosity, if you compare a cubic centimeter of a human flesh and a cubic centimeter of the center of the sun, the cubic centimeter of the center of the sun completely wins. Oh my gosh! As a matter of fact, a cubic centimeter of the sun's core gives off 5 quadrillion times as much energy as a cubic centimeter of human flesh. And that's because it is so hot, and so density plays into this as well. So basically, in this case, the legend is totally blown away, because the sun totally blows away a human as long as you're getting down into the core. Okay, I didn't see anything new there on Twitter. Let me go back down to let me scroll down to the bottom of the page here. Yeah, people are commenting on that. Okay, let me jump down here. La da da. Oh, somebody's saying you guys didn't hear the dog. Well, that figures. Let's see. Here's a great question. A little bit more philosophical than fact-based. But Titan Miller, really? Titan? Awesome. Asks, Phil, do you think that having a scientist, a true scientist, as president would improve the future of our country? No. No. Maybe. Yes. No. No, I'm doing that on purpose. I would rather have a scientist than somebody who has no experience governing or whatever. All things being equal, somebody with a science background would be great. But I think in general, I'd rather have somebody who is very familiar with politics. I don't want somebody who's overly political, and is willing to do something. Well, I don't know how to phrase this exactly, but what I mean is, the idea of politics is the art of negotiation, right? Of making sure that everybody's happy with the deals that are being made and trying to do the best for everybody. That's what politics should be. Scientists aren't necessarily good at that. Scientists are good at doing science. And of course, there are scientists who are great politicians. We have Rush Holt, I believe, is a representative from Illinois, I want to say. So there are scientists in Congress, and we have some scientists, some people with scientific backgrounds in government here in the United States as well. I know in Germany and England that's happened as well. But scientists don't necessarily make good managers. I've had good managers who were scientists and bad managers who were scientists in my own career, just like anybody else, right? Some people make good managers, some people don't. So all things being equal, there's no reason to think a scientist would be a better manager than anybody else. I want somebody who understands economics. I want somebody who can negotiate treaties with China and these other people. That would be great. So in general, no, that's not. If somebody say, would your first single issue thing in a politician be science? And the answer is no. I would rather have somebody who is not familiar with science as president, but who appreciates science, who understands science, who understands science's role in, well, everything, right? Somebody who says, yeah, global warming's real and humans are behind it. Somebody who says, yes, evolution is correct and creationism is baloney. Somebody who understands all this kind of stuff, the scientific process, critical thinking, and is able to apply it to certain issues. That would be fantastic. I would love that. Just what that would do for women's rights, oh my gosh, would be fantastic, let alone everything else we're dealing with in this country. As I speak, Indiana just passed a law making it legal to teach creationism in the classroom, which is insane. It's such a violation of the First Amendment. Anyway, so I wouldn't necessarily want a scientist, but I do want somebody who appreciates and understands and respects the science. Two different things. So there you go. Phil, you should run for president. No. Joe Albert. You don't want me for president. I remember when NASA was looking for a new administrator a couple of years ago, and there was a website where you could nominate people, and Bill Nye was in there, Neil Tyson. People were nominating a lot of scientists. People nominated me, and I wrote a blog post that said, you don't want to do that, because I'll be up front. If you want me to run NASA, what I will do is cash a check for $1 billion and disappear. That's my campaign promise. I will extort money and leave. Josh Meyer asks, Phil, can you pronounce the name of your favorite star? I assume you mean Zubin Esh-Shamali and Zubin El-Janubi. These are two stars in Libra, actually. They used to be part of Scorpius. It used to be sort of part of the claws of Scorpius, but they turned those into their own constellation of Libra, which is just a diamond shape. It's a useless constellation as far as those things go. But the two bright stars in it are, I think the names mean Northern and Southern Claw. I have to look that up, and I won't bore you by looking that up now. You can do that yourself. You look up Alpha and Beta Libra. But it's Zubin El-Janubi and Zubin Esh-Shamali, which I like. You guys are asking me some questions I can't really answer. If I don't answer your question, it may be that I've answered it before, or I don't know the answer, and I'd have to look it up, and I don't want to waste your time here doing that. And also, sometimes it's just easy to Google a question. I get questions in email all the time, people asking me, how much bigger is the sun than the moon? It's like, really? Let me Google that for you. So it gets, some of these questions are pretty easy to answer just by looking them up. Here's an interesting question. Here's one. Here's a good example of a question I don't know the answer to, but I can tell you a little bit of background about it. And Johnny Gratterall Guevara, is that right? Gratterall? I'm so terrible with names. Who asks, for how long will the moon orbit the Earth? Thank you for not ending that with a preposition, which is a silly holdover from Latin grammar, but who cares? For how long will the moon orbit the Earth? And what will happen when and if we lose the moon as a satellite? What will be the impact of life on Earth? Well, this is pretty interesting. You can see my T-shirt. I like the T-shirt. It's Venkman. Back off, man. I'm a scientist. The moon is orbiting the Earth, and the gravity of the Earth is holding basically the moon as it goes around the Earth. You know what? I've got the wrong window open. Let me put my there we go. Now I can see myself, so if I can hold these upright. So not to scale, right? The moon is about a quarter the size of the Earth, so it's really tiny. You know what? I've got a smaller dude here. I'll use my ping pong ball of science. I actually use this ping pong ball on a TV show. I need to find out if that ever aired. We're doing a scale model of the solar system, and I had ping pong balls down for the planets. This is not quite to scale. This would be about the size of Mars compared to the Earth, but close enough. So the moon is going around the Earth, and what's happening is the gravity of the moon affects the Earth as well, and gravity depends on distance. So the moon here is pulling a little bit harder on the near side of the Earth than it is on the far side of the Earth. And if you do the math, and I won't go into it because I've written about this, if you look up tides on batastronomy.com on my original website, you'll find a lengthy description of this. But basically, because gravity depends on distance, the moon is pulling a little bit harder on this side than this side. And if you do all the math, it's as if the Earth is being stretched a little bit. It's being pulled out this way and this way. And so the Earth is kind of egg-shaped a little bit. I don't know if I can, like that. Not very much. The solid Earth is only being stretched out by about 50 centimeters, roughly, between, as the Earth is spinning underneath the moon, different parts of it are closest to the moon, so they get pulled up, and then when they get around to being 90 degrees from the moon, they're at their most low, they're at their lowest point. Low. You can think of it. You don't have to think of it as it is tides. The part under the moon is high tide, and the part on the opposite side of the Earth is high tide, and the parts at 90 degrees are low tide. And it's a lot more complicated than that. I'm just summing things up very rapidly here. So when you're here, you're actually up a little bit higher by about 50 centimeters than when you're on the low tide part of the Earth. But what's happening is, as the Earth is spinning, it's stretching back and forth, and that's basically you need energy to do that. You're performing work on the Earth, and that takes energy, all the physics and stuff. And where that energy is coming from, it turns out, when you look at all the physics of it, is the orbital energy of the moon. So you're basically taking orbital energy of the moon and putting it into the Earth. And what that's doing is, oh no, wait a minute. Oh gosh, have I confused myself again? Oh yes, of course. At the same time, the Earth is doing this to the moon. The Earth's gravity is much stronger because it has 80 times the mass of the moon, and so it's pulling on the moon as well. Oh well, I just lost the moon. The moon is now behind my desk. So what's happening when you work all this stuff out, and there's energy being transferred back and forth and all this kind of stuff. But what's happening is that in the end you're not. I want to make sure the problem is not getting this right, is explaining it correctly. I guess in the end what you're doing is you're pumping energy into the moon's orbit, and so the Earth, you're stealing energy from the Earth. So the Earth's rotation is actually slowing down over time. The Earth used to spin much faster. But as the moon's tides and the Earth's tides on the moon have affected each other, the Earth has slowed down. And what that's doing is it's pumping energy into the moon's orbit. So the moon is getting farther and farther from the Earth. When you add energy to an object in its orbit, its orbit gets bigger. And when you take energy away from something that's spinning, it spins slower. So the moon used to be much closer to the Earth, and the Earth used to be spinning much faster, and the tides used to be huge. But the Earth has slowed down, and as that's happened, the moon is moving away. Now we know, we can measure this. The moon is moving away from the Earth by about 4 centimeters a year. And I happen to have my handy ruler. This is actually from the Far Ultraviolet Spectroscopic Explorer, an old mission from NASA, FUSE. Here's 4 centimeters right here, right about that much, right there. So the entire moon, which is, how big is the moon? 3,500 kilometers across, something like that, 2,000 miles across, is moving away from the Earth by about this much every year. Not a whole lot. Your fingernails grow at about that rate. So that's how fast the moon is moving away from the Earth. And so over time, it's getting farther and farther and farther away. And remember when the guy asked me the question like an hour ago, and I started answering it? Oh my gosh. Eventually, if all things are equal, the moon is just going to drift away from the Earth. It'll be so far away that the gravity of the sun will be more of an influence on it, and it'll just orbit the sun. But it's more complicated than that, because it turns out the sun has gravity on the Earth and the moon, and there's tides from that as well. There's energy being pumped into and taken away from the Earth-Moon system, and blah 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 blah. The thing is, I'm not clear on what's going to happen a long time from now. The Earth is slowing its spin, and the moon is moving away. Eventually, the moon will move far enough away that the Earth's spin will lock with the moon. Right now, you can see the label there on the moon. Do I want to get into this? If the moon didn't spin, you would always see that label, right, as it goes around the Earth. But that's not what happens. The moon does spin. It spins once for every time it goes around the Earth. And so if I spin the moon in my hand, I can keep that label, for example, pointing toward the Earth. From the Earth's point of view, I've got the moon spinning, and so that label always points toward it. And that's what's happening. Because of this tidal interaction, the moon spins once for every one time it goes around the Earth, and that's why we always see the same phase. That's going to happen eventually with the Earth. The Earth is going to slow its spin, the moon is going to move out, and eventually the Earth will spin at the same rate the moon's going around the Earth, and they won't be swapping energy anymore. The moon won't be receding from the Earth. But there's still the sun pumping energy into the system, and there are other things going on, and that is so far in the future, billions of years in the future, that I'm not sure what's going to happen. So the thing is, the reason I wanted to answer this question is because there's all kinds of cool stuff going on. The dance of the Earth and the moon is very complicated. They're exchanging energy. There's all kinds of crazy stuff going on. But the end point of this, I don't think, is all that well understood. And the timing is critically important. If it takes more than 6 billion years for the moon to recede to the Earth to the point where they're tidally locked and the Earth is rotating at the same time it takes the moon to go around the Earth, the sun's going to swell up into a red giant and engulf them both. The problem is the sun is losing mass all this time, and so it's losing gravity, and the Earth and the moon are moving away from the sun very slowly. 6 billion years from now, we'll be much farther away from the sun than we are now. So when it swells up into the red giant, we don't know if it's going to engulf the Earth or not. There are actually people who are arguing back and forth on this. We don't quite know enough about how stars evolve with time to know if the Earth's going to get consumed or not. We do know the sun will expand. We just don't know if the Earth is going to move away far enough to be saved. It'll be broiled one way or another. So there's all this complicated stuff going on. And so the end point here is, I don't know. There's a lot of things going on. It's really fun and interesting to think about. But what's going to happen in the end product, I don't know. Well, certainly I don't know. There may be studies out there that have a better answer than I do. But there you go. All right, you know what? It is noon my time, which makes it 1900 UTC, which means I've just been blathering on as usual. Parker Mills in the Google Plus page with all the comments on it has linked to my blog post about human beings being brighter than the sun. Thank you very much. That's very convenient. Feel free to do that. If you find a link or something, dump it into a comment so people can see it. Let's see. I'll refresh the page. Oh my gosh, look at all these questions now. I really only have time to take one more. So let me scroll down. Trying to find something I can answer quickly. What's my favorite Star Trek TNG episode? Best of Both Worlds. I love that one, the two-parter with the Borg. I like the season finale. All Good Things. Everybody always says Inner Light and Yesterday's Enterprise. Those are excellent, excellent episodes. But I think the Borg one was my favorite. Do stars flicker? If so, why? Oh, that's Paul Hill's asking a question. That one's really easy to answer because I wrote about this on Friday. Go to my blog on Friday. I have a blog post called Seriously Twinkling, and I talk about why stars twinkle there. Somebody linked, Parker Mills again, linked to my Tides post on Bad Astronomy. Thank you very much. I'm just trying to find a good question. Is there anything on... Oh, you know what? Here's a good question. On Twitter, from Dragum, or Drawgem, probably Dragum, who asks, is it possible for the Earth to have an extra moon? Will it destroy mankind? If it's a Death Star, then yes. I get a question similar to this a lot. Can moons have moons? And the answer is yes. And the trivial answer to that is we have satellites orbiting the moon right now. Lunar Reconnaissance Orbiter. Gosh, is the Indian probe Chandrayaan-1 still orbiting the moon, or did they crash that into the moon? I can't remember. We've crashed many probes into the moon on purpose to try to make craters and look for different chemicals, including water, on the moon. But there's still several orbiting. Lunar Reconnaissance Orbiter is still orbiting the moon. The Grail probes, Ebb and Flow, they were just renamed to Ebb and Flow by some school kids in Montana. And those are orbiting the moon. So artificial satellites, sure. But you could replace those with just a rock, and those would orbit the moon. We have satellites orbiting the Earth, right? There are thousands of satellites orbiting the Earth. Now the thing is, they're very close to the Earth. We can go back to my twin models of the Earth and Moon of science here. I know I stole that from mine, but what the heck? Moon is pretty far from the Earth. The moon's about 3,500 kilometers across and 400,000 kilometers away, 2,000 miles across. 280,000 miles away, something like that. It's very, very roughly isn't it 100 times its own diameter away from us? But the point is, it's quite far off, farther off than you might expect. So its gravity, if you were to try to put a satellite here directly in between them, every time it goes around the Earth, the moon's gravity would tug on it, and eventually it would change that orbit, and it would either fling the satellite away or it would crash into the Earth or the moon. If you keep a satellite really close to the surface of the Earth, it can orbit there for a long time, and the moon's influence on it is very, very, very tiny. So if you put a satellite up, say 400 or 500, well, more than that, let's say 1,000 kilometers up, well above the Earth's atmosphere, but still very, very, very far away from the moon. The moon is still 100 times farther away or more. The moon's gravitational influence on that satellite is very low, and so that satellite's orbit can be stable for centuries or millennia. Of course, if you put little rockets on it, you can adjust for that. But the farther out you get from the Earth, the more the moon's gravity influences you, and the same is true for the moon. You want to have satellites orbiting the moon very close, because if they're farther away, the Earth's gravity, which is much larger, will affect them. But there are stable orbits. So, and you know that for a fact because we have all those satellites up there. And in fact, our weather satellites, our communications satellites, are 40,000 kilometers from the Earth, 22,000 miles, something like that. And they stay stable right there for very long periods of time. So, and in fact, there are also these points of gravitational equilibrium called the Lagrange points, where the moon's gravity and the Earth's gravity are the same, and so sort of all three of them orbit the sun as a triad. And there are these different points for all that, and it's craziness. So the point is, yes, you can have. The Earth could easily have more satellites. And again, I guess another trivial answer to this would be, well, sure, Mars is smaller than the Earth, right? And it has two moons, Phobos and Deimos, or Deimos, or Deimos, however you want to pronounce it. I believe it's Deimos. Jupiter has a gazillion satellites. The more gravity you have, the more satellites you can have, but just in general. But the Earth easily could have more satellites. Could it destroy the Earth? Yes, in fact. You can imagine if we had I don't know, a smaller moon, let's say an asteroid 5 miles across to 8 kilometers across, were to somehow move into an Earth orbit. Over time, the moon's gravity could change that thing's orbit until eventually it smacks into the Earth. You don't want that to happen. That's the size of Mount Everest smacking into us. That would be bad. On the other hand, if we decide to move an asteroid into Earth orbit, and there are ways of doing that. I described that all over the place. I gave a TED talk about this recently, as a matter of fact. There are ways of tugging an asteroid into an orbit. You could take it, put it into an Earth orbit, and keep that gravity, you keep the rocket tug there so that you can adjust the orbit of that asteroid. If it starts getting a little too wonky, put it back into its safe orbit. And then you could have satellites that stay stable for forever, as long as you want them to. It's an interesting point, because that might be someplace people could live. It might be something you could mine for minerals. I've seen studies that show that we could be rich that way. I've seen studies that show that you can't do it. It's too expensive. If you have cheap access to space, it becomes easy to do that. So, the idea of another moon of the Earth would be fascinating. Oh, and I'll end this with one more thing. You sometimes hear about these second satellites of the Earth, like Cruithne, which is Cruithne. Cruithne. It's a Gaelic name, and I think it's Cruithne. It's very difficult for Westerners with big stupid tongues like me to pronounce. But it turns out you hear about these, a second moon of the Earth, but they're not really moons of the Earth. They're orbiting the sun in an orbit that's similar to, but a little bit different than the Earth. And so from the solar point of view, we're both going around the sun. But from the Earth's point of view, it's almost as if this thing is going around us. It's two different views. It's kind of like somebody. I'm trying to think of where you might have two different point of views. Like if you're driving in a car and you turn left, it kind of feels like there's a force pushing you to the right, centrifugal force. But to somebody standing outside the car, they see you trying to go straight and the car pushing you to the left. So, excuse me. And I just said that wrong, didn't I? If you're turning to the left, if you're inside the car, it's like you feel a force to the right. That's not really the case if you're standing outside the car. You see somebody trying to go straight inside the car, but the car is turning left and pushing them to the left. The person inside feels that as a force to the left, to the right. To you standing outside, the person feels the force. To you standing outside, you can see that they're being pushed to the left. Centripetal versus centrifugal. I need more coffee, apparently, today. So the point is, what you see depends on where you're seeing it. It's a point of view thing. You know, a better example, stupid of course, standing on the surface of the Earth, we see the sun rise, get up high, and then set, right? So it feels as if the Earth's not moving and the sun's going around us. But we know that if you were outside the Earth, it's just the spin of the Earth making the sun rise and set. It's a geocentric versus a heliocentric point of view. They're both legitimate. They both have their uses. Which one is more real just depends on what you're trying to do. If you're trying to get up when the sun comes up, sure, use a geocentric frame of reference. Who cares? If you're trying to send a probe to another planet, using a heliocentric frame of reference makes things a lot easier. It makes the math a lot easier. And it's the same thing here with these moons of Earth. It makes more sense to think of them as going around the sun in a similar orbit to the Earth. But from the Earth, from our point of view, it kind of looks like they're going around us and approaching and receding. It's interesting, and you can look these up. I've written about them. I've written about if anybody's Gaelic in the chat room, and you can write this out phonetically, please feel free. I know it's on Wikipedia, and there's even a pronunciation. Bob Daniels actually put it in Wikipedia. Put the Wikipedia link. Let's see if I can play this. Oh, it gives the pronunciation, and there's a little speaker symbol, but it doesn't actually say it. Oh well, I was hoping they'd have a little audio clip where it would say "Kroitny" or whatever it is. But you can look that up, and I've written about it as well, and you can see the two different views, and it makes perfect sense. If you can think three-dimensionally, which can actually be a little bit tough, or at least think outside of looking down on things that are all moving around. It's very confusing. I had a conversation with my wife and daughter yesterday. We were talking about the moon always facing the Earth and all that. And it's amazing how difficult it is for us to grasp that. I have huge amounts of practice. I've been doing this for years, and I still can trip myself up like I did a couple of minutes ago. It's fun. It's fun to think about. You get better at it with time. Okay, looks like the Twitter stuff is dying down. So let me see. It looks like that's all the time we have, actually. I've run a little bit late. Shocker. It's because I've been looking stuff up and talking too long. But let me wrap this up with just a couple of things. You can find me at badastronomy.com, which will take you to my blog for Discover Magazine. I am on Google Plus as Philip Plait. You can also search under the Bad Astronomer now that they allow those kind of nicknames. I post on Twitter quite a bit as @badastronomy. Matter of fact, some people complain that I tweet too much. That's too bad. I don't care. I tweet as much as I want. It's my Twitter feed. And I post dumb jokes and all kinds of stuff there. So Twitter is for short things. The blog is for more in-depth science a lot of the times. Google Plus is sort of intermediate. I can sometimes give a little bit more opinion there and then link to other things. Thursday mornings at, I think at the same time, at 1800 UTC, which is morning to me. It's 11 in the morning on Thursday. Fraser Cain, Pamela Gay, John Voisey, Nicole Gugliucci, Emily Lakdawala, Ian O'Neill, Alan Boyle, I think, is everybody we've had so far. We do an astronomy roundup, astronomy and space news roundup, where we wrap up sort of the week's news, talk about it, discuss it, chat about it for an hour using live Google Hangouts. Look for Fraser Cain, Frasercain, or you can go, you circle him and he announces it. We all do. Or you can go to cosmoquest.org and watch it live there, cosmoquest.org. And I will continue to do these Q&BAs. I love doing these kind of things. I started doing these years ago, and it became too much of a hassle. Google Plus has now made it a whole lot easier for me to do this. I love being able to answer questions. I like it more when I do them correctly. But it's interesting to have to do this off the cuff sometimes, and it's amazing what'll trip you up. And what you think you know, and maybe you don't have as good a grasp of as you thought. But that's live, and that's science. Look, you know what happened here today? I made a couple of mistakes. I looked it up, and I was able to correct myself. It may have been confusing at the time, but at the end, hopefully you got the right answers, and you got, even more importantly, the references you need to go and find the right answers, because that's what science is all about, right? That's what skepticism is all about. I don't want to teach people this. You know, the moon is so big. A more interesting question is, how do we know the moon is that big? And if you have the tools to do that, that's how you'll learn, and that's how you can find out what's around that next corner. So thank you, everybody, for coming to my chat. I appreciate this. Keep your eyes open. I'll be editing this. This will be up. The whole thing will be up on YouTube soon. except for a couple of things I'll edit out because I don't want it to be too confusing. I might leave it in there just to keep me honest. I don't know. We'll see. But I'll be putting these up, and I will see you hopefully next week. So thank you again.